Hi, my name is John Williams and I am the research hydrologist with the USDA Agricultural Research Service in Adams, Oregon. Today I want to share with you the results of research that microbiologist Kate Reardon, soil scientist Stuart Wiest, and I conducted between 2013 and 2018. This research was funded by the USDA ARS Program in Sustainable Agricultural Systems. Our results will shortly be published under the title of Soil Water Infiltration after Oilseed Crop Introduction into a Pacific Northwest Winter Wheat Fallow Rotation in the Journal of Soil and Water Conservation. There are many more details about our findings in that article, and I encourage you to read it. We conducted this research at the Adams, Oregon Agricultural Experiment Station. This location is in the intermediate precipitation zone of the interior dryland cropping region of the Pacific Northwest. It receives 12 to 18 inches of precipitation in the form of snow, rain, and fog each year. We designed this research to examine two possible attributes of oilseed crops when introducing them into a wheat crop system. These potential attributes are A. Oilseed crops provide a biochemical, microbiological advantage to subsequent wheat crops, and B. that oilseed crops improve soil properties for water infiltration by the creation of biopores through the deterioration of their roots. I will report on the infiltration response, and Dr. Reardon will address the biochemical microbiological results in the future. We repeated our measurements 3 years, testing whether water infiltration rates were different following a single oilseed crop that was followed by a spring wheat crop. To reduce differences across the test site, it was chemically fallowed for 24 months, after which we planted treatment crops of winter wheat, winter canola, and spring Ethiopian mustard. A fall and winter chemical fallow followed harvest of the treatment crops. Spring wheat was then planted directly into the furrows of the treatment crops. Ponded infiltration tests followed harvest of the spring wheat. Our plot layout looked like this, with 18 crop furrows. The inner 4 furrows were planted to the treatment crops, and we conducted the infiltration tests on these inner 4 furrows, as shown in this image where the blue circles are. For those of you unfamiliar with ring infiltrometer tests, here's how it's done. First, you have to get the rings into the ground. The rings are driven 12 inches into the soil, a challenge with very dry August soils. For as long as I can remember, we've done it this way with a 20-pound slide hammer, and before that, a sledgehammer. The crew was good for about 12 to 18 rings per day, depending on how hot it was. New ideas are always welcome. After Dr. Reardon's brother Mike heard about what we were trying to do, he asked, wouldn't it be easier with a hydraulic post driver? It is, and with a few minor tweaks to the system by our farm manager, Steve Umbarger, we christened the machine Big Mike, and life got substantially easier. Our infiltration tests were conducted over a period of 2 hours. Here, Dr. Stuart Wiest is going over the test procedure with Caroline Mell, Ryan Lacey, and Dave Robertson. Water is ponded at a constant head or depth in the rings, and changes in the supply tube are recorded every 10 minutes after a preliminary 40-minute wet-up period. Once we had established steady-state infiltration rates, blue dye was added to the ponded water to determine if water was following root channel biopores left by the wheat, canola, or mustard crops. For our results, I'll begin with a comment on the production of winter canola in this region. Successful production of winter canola is dependent on a combination of precipitation, temperature, and day lengths to attain a growth stage capable of surviving extreme cold events through the winter without prematurely exhausting available soil water. As a result of poor conditions in 2 of the 3 years of the experiment, we had to reseed canola in the spring of 2015 and 2016. Based on our success rate, I can't say that I'm a big fan of winter canola. Our water infiltration tests show significantly higher infiltration rates following the oilseed crops. In this graph, you can see that the infiltration rates in canola and Ethiopian mustard are faster than in the winter wheat. Although these differences do not appear to be very substantial, a statistical contrast between the two oilseed crops versus winter wheat resulted in a p-value of less than 0.02 from a sample size of 24. A p-value this low is unusual for infiltrometer tests, particularly in this agricultural setting, making the statistical difference between the treatments all that more meaningful. We did not find evidence, that is to say narrow concentrations of dye, on the underside of the rings where water had percolated through the soil core. If we had, it would have been evidence of deteriorating root channels creating biopores. Typically, the ring bottoms looked like the following examples. First, in the canola treatment, there is a saturated soil, wet, glistening soil but not dye, in the lower left third of the core, but no visible signs of large canola-sized root pores or dye concentrations indicating biopore flow. In the mustard treatment, there are signs of saturated flow on the right side of the ring with dye penetration in the lower mid area of the ring, some of it near a pore. But generally, this wet glistened area indicates mass or dispersed flow, but not concentrated quick flow through biopores. Finally, in the winter wheat treatment, there is no sign of saturated flow through the ring, although you can see several macropores of indeterminate origin. Nonetheless, there was little, if any, obvious dye flow through the core. Our conclusion is that oilseed crops can increase water infiltration after only a single crop, but this is not the obvious result of biopore development. These results differ from those of research we conducted in the low precipitation zone of the inland Pacific Northwest and reported on in a companion video presented in this year's virtual field day. If you haven't watched that video, I invite you to do so. While these results are statistically significant, the real-world difference between the infiltration rates is relatively small. We suspect the changes in soil characteristics in the oilseed treatments might be cumulative with time in this precipitation zone, but long-term research would be needed to confirm these suspicions. In conclusion, Stuart, Kate, and I wish to thank Caroline Mell, Dave Robertson, Mandy Wiest, and Steve Umbarger, and the several seasoned employees who provided the technical support that made this research possible. This video was shot at home because of COVID-19. It would not have been possible without the in-house help of two of my closest family members. The manuscript reporting this research should be available online sometime in June, with the print version available in the November-December Volume 75, Issue 6 of the journal, or you can request a non-published version from one of the authors. We thank the Columbia Basin Agricultural Research Center, CBARC, Oregon State University, for providing a platform to present this video. On a final note, I will retire 30 June of this year, and I want to acknowledge with deep appreciation the producers and farm managers who allowed me to conduct research on privately owned property. The following is what I hope to be a complete list of those folks. Many are retired and some have passed. In either case, thank you and your families. Good day.